Hello, thanks for joining me. We're going to talk today about number sets, and that we're going to approach them from a different angle. We're going to approach them from the angle of operations. So let me write this down here. Operations. So we're going to look at our operations, and you remember what those are. Well, you know, the addition, and then subtraction, and then multiplication, let's say multiply, and then division. But I'm going to start with one you may not have thought about before, and that is the first one, which is counting. You see, operations are just a way of finding out how much we have. How much stuff do I have? And the most basic way to find out how much stuff I have is by counting. And it is in the process of figuring out how much stuff I have that I have to create or come up with number sets. And number sets are just different groups of numbers that I can use to count stuff. Now, the most basic number set, you already know about. It's the one that goes like this. I'll put it in set notation. 1, 2, 3, 4, and so on. And that's the one that you use when you're counting on your fingers and maybe your toes and maybe your neighbor's fingers and toes. It's really natural. It's really natural to just, you throw a bunch of things on the table and then you can count them using these numbers, and these are called the natural numbers. And let's just talk about kind of the characteristics of the natural numbers. Notice they start with the number 1, and you go up from there. So you count up, but you don't count down. You just count up, and you go up each time by an amount that is 1. So you go up by 1. 1 plus 1 is 2, and 2 plus 1 is 3, and 3 plus 1 is 4. And then you keep on going. And it turns out that even though this number set, which is we're going to see is fairly restricted, it's an infinite number set. It goes on forever. You can count all your fingers, all your toes, all your family's fingers and toes, and all your neighbors, and everyone in your city and your state, and the country, and the planet, and the universe. And it just keeps on going and going and going. Those are natural numbers. Now, those seem like perfectly fine set of numbers. It describes everything that we ever wanted to count. You can count the number of hairs on your head if you want to using natural numbers. But there's, as you can imagine, as you already know, there ends up being some problems with this, with natural numbers. So let's see how that came about. And to do that, we're going to start taking some shortcuts. And so the first shortcut that we're going to do is we're going to do a shortcut of addition, right? You're counting, you count it out. I've got 15 things on the table here, and then on your table there's 7 more things, and somebody said at some point, hey, wouldn't it be nice if we could just do, 15 plus 7 instead of having to start over again, right? If you put all my 15 things and your 7 things together, wouldn't it be nice to not have to just start over from 1 and count all the way up to, what would that be, 22? So that's where addition came from. It's just a way of kind of doing the counting in stages. I'm going to count these, and then I'm going to count those, and then I'm going to add them together, and I'm not going to have to recount. I'll just add them up. We'll have some rules for addition. Now, that's really nice and handy, and it turns out that as you add up natural numbers, you just get more natural numbers. Right? 15 plus 7 is 22, natural number. 4 plus 3 is 7, a natural number, and everything is fine. But then somebody said, well, what if I added something and then I made a mistake. I didn't mean to add it. What if I want to undo my addition? And so we came up with subtraction. Subtraction undoes addition. It works like this. You know how it works. If I added two things together and I got 22 and I said, no, I take it back. I don't want to add 7. I'm going to subtract 7. I want to know how many did I have before I added those 7. And of course, 22 minus 7 is 15. Now, this is perfectly fine as long as I restrict myself to doing subtraction problems that are the reverse or the opposite of addition problems. But somebody came along and said, what if I do a subtraction problem that didn't come from an initial addition problem? What if I do one that I made up like this? What if I did 15 minus 15? Now, there's no addition problem where I said 15 plus something equals 15, but I made up this subtraction problem, and I have to come up with an answer for that. Now, you know what the answer is, because you're sophisticated, you're a math sophisticate. You know that the answer is 0. But it is actually quite a revolutionary thing that somebody said, you know what, let's have a concept for 0, right? Can you count 0 objects? Like, can you put 0 things on the table and count them? And it turns out that's a little bit tricky to do because you can't hold 0 things in your hand. I don't know, maybe you just have an empty hand, but that's such a revolutionary idea that many ancient civilizations didn't even have the idea of 0, and it was a big deal when 0 was invented, and that's why we created a number set that just acknowledges the existence of the number 0, and we call that number set the whole numbers. Whole numbers. And it's the set that takes our natural number set of numbers and adds to it the number 0. So 0, 1, 2, 3, and so on. So it's also an infinite set of numbers. And it comes out of this idea of subtracting what was never added, it was never an addition problem. I never had the idea of saying 15 plus 0 equals 15 because I didn't have the number 0 in the natural numbers, but then when I went in and misapplied subtraction, I got 0. Well, you probably can see where this is going. What if I said not 15 minus 15, but what if I said 7 minus 15? Now, again, you are a math sophisticate. You know the answer to that question. But if you think about it, under the whole numbers, there is no answer to that question. There is no number that is 7 minus 15 if you're only talking about whole numbers. In order to get the answer to this question, we have to come up with a whole new set of numbers, and we're going to call those the integers. And the integers, as you know, include negative numbers. Okay, I'm tired of writing numbers. There you go. There's the set of numbers. And notice that this set contains all of the whole numbers, 0, 1, 2, 3, 4, 5, and so on. And all of the counting numbers, or the natural numbers, are in there, 1, 2, 3, 4, 5. Plus, there's a bunch of numbers that are the same as the natural numbers, only negative. So for every natural number, 1, 2, 3, there's a negative number matching that, negative 1, negative 2, negative 3, and so on. So this set is infinite, but it's infinite in both directions. It goes up in the bigger direction, positive, and down in the bigger negative direction. And now we can answer the question, negative 8. 7 minus 15 is negative 8. Okay, well, you can see that there was a lot of mischief done with that opposite operation of subtraction when we subtracted. We did subtraction problems that did not come from a natural number addition problem. We got ourselves into all kinds of trouble. Well, that's going to play out again big time in this next shortcut. Because after a while, people are like, hey, let's do 3 plus 3 plus 3 plus 3. And somebody said, this is getting tedious. We're doing the same number over and over and over again. Couldn't we shorten that? And you guessed it. They said, couldn't we just say 3 4 times? Or 3 times 4? And so the next shortcut was multiplication. Multiplication is a way of doing repeated addition of the same number over and over and over again. So 3 plus 3 plus 3 plus 3 is 3 times 4, which is 12, and 3 plus 3 plus 3 plus 3 is also 12. So you can check it. It works. It's a shortcut. Multiplication is a shortcut for addition. That's literally what it is. It's just a way of doing repeated additions over and over again, and therefore it helps us to do math a little bit faster. We don't have to do quite so much addition when we're doing multiplication. And then someone said, well, if we're going to do multiplication, we have to have a way of going back. What if I said 3 times 4 is 12, and then I changed my mind and said, no, I just wanted to not multiply by 3. So 12, what happened? What was that 12 before I multiplied it by 4? So we're going to divide by 4. And we get back to where we started, 3. So division undoes the multiplication, right? You know this. So division and multiplication are opposite operations. Very simple idea. Now you can see what's going to happen. Some joker came along and said, well, what if we do not 12 divided by 4, which is 3, or 12 divided by 3, which is 4. That's all perfectly fine. Both are undoing multiplication that we'd already done with integers. Somebody said, what if we do 3 divided by 4? And of course, we never had a problem that said something times 3 equals, no, something times 4 equals 3. Like there was never that problem. Something times 4 equals 3. And so what is the answer to that problem? Well, it turns out the answer to that problem, 3 divided by 4, is in none of the number sets we have. Integers, whole numbers, natural numbers none of them contain the answer to that problem, 3 divided by 4. And way back in 4th grade or 5th grade or whenever you started doing fractions, you probably would have been willing to say, well, that's fine. Let's just stop math right there and not do. Let's just say that these are all the numbers we need and not use any more kinds of numbers. But they didn't let it go, and so we came up with numbers like 3 divided by 4, and in fact, like that's not even a number, 3/4. It's just a math problem. 3 divided by 4. That's what that is. And we could do 4 divided by 3. We could have negatives. Negative 12/13. Now, what's the first one? What's the first fraction? Oh, we could write them as decimals, right? 0.1. But what's the first fraction? What is the first fraction? Where do you start? Let's just say the first one bigger than 0 to make it easy. Think about that. What's the first fraction bigger than 0? Well, it turns out that you can't think of it, right? Let's just say you said 0.0001, which is the same as 1, I think that's 1/10,000th. Well, I say there's a smaller one than that. There's one closer to 0 than that, of course. So I would just say 0.00001. And then you would say, well, 0.000001, and it would just go on forever. So there is no smallest fraction There's no smallest positive fraction. There's no way to start the list of fractions or decimals or parts or pieces, and therefore we're going to have to stop listing. We're going to have to stop listing our fractions here. We can't list these. Let's see. Let me get my nice big eraser here, and I'm just going to erase all these numbers. Oops, erase this. Okay, so I'm just erasing my numbers because I can't list them. Now, you know what they're called. They are called the rational numbers. And rational numbers are fractions. They can be written as fractions or decimals. They can be written as decimals, but they're much more useful as fractions. We're going to say they can be written as a number, an integer a, over another integer b. And so they can be positive, negative, they can be integers, top and bottom in the fraction. That's the best representation. Notice that way of writing them is a ratio a to b, a over b, a divided by b. It all means the same thing. And so rational numbers. Now, we had to deal with what happens if our number on top is bigger, what happens if the number on top is smaller, what happens if we try to turn it into a decimal. Remember, there's this issue with repeating decimals, right? 0.33333 repeating forever. That's 1/3. And what about a terminating decimal? That's like 0.125. So we could talk a while about rational numbers and what they look like, and then how do you add them together and subtract them and multiply them and divide them. That was a huge part of grade school mathematics, was just trying to figure out how to deal with these rational numbers, doing long division with decimals and all that stuff. But that's where those numbers come from. It comes from the misapplication of division, where you're doing a division problem that didn't come from a previous multiplication problem using integers. Okay, that's a kind of a big deal. But now let's slide down here, and we've tried ratios, rational numbers that have negatives in them and positives, and we said, okay, everything, we tried out all the different things that can happen, but there's one we didn't try out, and you may be thinking about this one. What about, we did 3 divided by 4, but what about 3 divided by 0? Now, we've got two choices here. Every time we do a misapplication of a shortcut, a division or subtraction so far, we either come up with a new number, but we do have a second option, and that is to just say, hold the phone, we're not going to let that one fly. And that's what mathematicians said here. They said, okay, we let you have 0, we let you have negative numbers, we let you have fractions, whatever those are, but we're not going to let you have something divided by nothing. And so we're not going to do that. So in our rational number definition, a over b, we have to say that b cannot equal 0. We're not going to go down the road of having a number divided by 0. So we'll never divide by 0. Well, that's kind of nice. We didn't end up with even more number sets here. That's kind of cool. All right, now the next few steps we're going to take us way beyond, way deep into math, right? Up to now, this is grade school math. Now we're going to get a little bit, more esoteric, and I'm going to erase some stuff here just because I need a little bit more space over here. But what's the shortcut to multiplication? Remember, the shortcut for counting was addition, the shortcut for addition was multiplication. But what if I have a problem, let's say it's 2 times 2 times 2, right? So multiple multiplications of 2. 2 times 2 times 2. Is there a shortcut for that? Is there a quicker way to say that? And the shortcut is 2 to the third power. So if you haven't got to powers yet, don't worry about this. Just understand that it's a shortcut for multiplication. We call these powers. We're really familiar with the squared power, right? 3 squared just means 3 times 3, which is 9. 5 squared is 5 times 5, which is 25. But all the powers, and we can use any number for a power, and all of them are shortcuts for multiplication. They're kind of useful. They're very useful, actually. Well, what is the opposite of power? What if I did 5 squared is 25, and now I've got this 25, and I said, I want to unsquare it. I want to go back. I want to not square it. I want to find out what I had before. I want to get back to 5. And it turns out the opposite of powers, squared, is the square root. So we're going to say the opposite of powers are roots, because we can have roots that are square roots, but we could also have cube roots, with the power of 3, right? 2 cubes, so the 2 cubed is 8, and the cube root of 8 is 2, because you're undoing the cube. And we can have roots with higher bases in them, or higher roots, 4th roots, 5th roots, so on and so forth. So roots and undo powers. Powers are a shortcut for multiplication. And now we need to go through this process again of what if we come along and we do the root of a number that didn't originate with a power. Now, think about this. We'll just do a simple example. If I say 2 squared is 4, and 3 squared is 9, let's think of a number in between, right? So the square root of 4 is 2. The square root of 9 is 3. But what's the square root of 5? 5 is between 4 and 9, so there needs to be a number between 2 and 3. That if we multiply it by itself, we get 5. But what is that number? And it turns out that number doesn't exist. There is no number that if you square it, you'll get 5. A thing by itself equals 5. And it turns out, if you think about this, this makes perfect sense. There's only a limited number of perfect squares, right? 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16. So 1, 4, 9, and 16 are perfect squares, but all the numbers in between them are not perfect squares, right? 2 isn't a perfect square, 3 isn't, 5 isn't, 6, 7. So the square root of all those numbers doesn't exist within our set of numbers here, our rational, integers, whole numbers, natural numbers. So we had to create a new set of numbers, and we call these irrational numbers. Now, the nice thing about irrational numbers is they are completely separate from the rational numbers. They're numbers that are not rational. Rational numbers can be written as fractions, or they can be written as decimals that either end, terminate, or repeat. So irrational numbers don't do that. They cannot be written as a fraction, and they don't terminate as in the decimal form, and they don't repeat in the decimal form. Some famous ones are the square root of 2, square root of, my pen stopped working. Square root of 3, and pi, and you may have heard of e. There's a whole bunch of them. Those are irrational numbers. That's where they come from. The misapplication of roots as a shortcut to a power, but doing it in a place where there was no power to begin with. There was no power operation to begin with to get that number, to get that answer. So that's irrational numbers. Now, just really quickly, because this is way deep weeds, but we said, what if we do the square root of some numbers between the powers, right? 1 squared, 2 squared, 3 squared, 4 squared. and what's the numbers in between the answers. But what if we did the square root of negative 4, let's say? Now, obviously, square root of 4 is 2, but there's no number, if you multiply it by itself, that equals negative 4. 2 times 2 is 4. Negative 2 times negative 2 is also 4. So there's no number that you can do the square root of and get, or you can square it and get negative 4. So that created this whole new set of numbers, which we'll talk about in Algebra 2 and beyond, which are called imaginary numbers. And that comes from the misapplication of roots, specifically square roots, to negative numbers. Okay, and imaginary numbers contain the square root of negative 1 as one of its factors, and we use the letter I to represent that. And then we're getting to the end, but I will just mention that we can take those numbers and combine them with all the other numbers and create what are called complex numbers. And complex numbers include imaginary part and a non-imaginary part. So that is, and we'll say A plus BI, so that A is one of these irrational or rational numbers, and then B is one of those rational or irrational numbers multiplied by I, which is an imaginary number. That's really deep weeds. Don't worry about that. But I just wanted to, I want you to see that there's this whole progression in math from very simple natural numbers, 1, 2, 3, using operations to answer the question, how many do I have? And then trying to do a shortcut so that, and the shortcut is so we can do more complex math. And so as we do these shortcuts, we end up creating whole sets of numbers. Now, there's one thing I want to show you real quick. First of all, the numbers that we started talking about are the real numbers. Natural numbers, and then whole numbers are including the natural numbers, and then integers are all the whole numbers plus some negative numbers, and then rational numbers are all the integers plus all the fractions, the numbers of the denominator that's different than 1. And then we had the irrational numbers, and they were kind of defined as not being rational, so they're a whole different category. But all of these numbers can be written on the number line. All of them can be used to indicate an amount. And so we call them real numbers. And then, of course, imaginary numbers are not real. They cannot be used to count things in the natural world or the real world. So we call those imaginary numbers, and that gets really esoteric. And then putting real numbers and imaginary numbers together are called complex numbers. So that's the way they interact with one another. And that's it. Thank you for watching this. Let me take you down to a place where I have all of this written out nice and neat. And you can pause the recording and you can write this down. I'll point out that for some of the number sets we have letters that they're kind of like capital letters, often with some sort of fancy script. So capital R, when we say over R, we mean the set of real numbers, so all the different kinds of rational and irrational numbers. N stands for the natural numbers, W for the whole numbers, and then Z, of course, stands for integers. Don't ask me to explain that one. Q stands for rational numbers, and I stands for irrational numbers. Again, I don't know where the Q comes from, but if you see a kind of a statement about solve this over N or solve this over W or Z, it's saying find your solution, but you're only allowed to use these kinds of numbers, the numbers in this set, not all the numbers that exist. And that happens a lot, especially if we're dealing with a problem that ends up with imaginary numbers as the solution. To begin with, we'll just say, well, we'll just throw those answers out when they don't exist, even though we could talk about imaginary numbers. We're just going to say we don't acknowledge their existence. But in some cases, we don't acknowledge the existence of irrational numbers or rational numbers. How many people can we fit inside the car? Well, we're not going to say the answer is 3 1/4 because we're not going to deal with chopping people up. So there's situations where we confine ourselves to certain sets of numbers, and that's why we need to kind of have them labeled and figure out what we're talking about with these different kinds of numbers. All right, well, that's enough for today. Thank you so much for watching, and have a wonderful day.